All right, good afternoon, guys. Excuse me, I'm sorry I'm not there today, but today we're going to carry on with lesson 4.3, which I correctly titled up there and messed up here, in our unit on trigonometry. And this is about something called special angles and the unit circle. But no one should be intimidated. It's basically about specific cases where we can know the exact sine, cosine, or tangent of an angle. Not the sort of messy decimal that usually gets spit out by a calculator, but cases where an angle gives you an exact, precise, rational number for sine, cos, or tan. And we call these special angles. And to learn about them, we're going to put angles on the xy plane. And specifically, we're going to put them on the xy plane like this. That's the x-axis, that's the y-axis. We're going to start at the origin, right here in the middle, and we're going to draw a line out like this. And we're going to define that line as being exactly 1 unit long. And from this point, I want to kind of follow it down to the x-axis and across to the origin. So we end up with a right angle triangle. So we're going to do some right angle triangle like this. So we're always going to define, when working with this, we're going to define our angle as the angle between the x-axis and the line going counterclockwise. So theta is the angle between the x-axis and the line anti-clockwise. So that's the basic setup. And what I want you to keep in mind is if we've set this up completely artificially, if we've imagined an angle being a line that goes from the origin out at an angle from the x-axis, we've made a right angle triangle with an unknown angle theta. And if we've done that, we can name all of these sides. And of course, this side would be the opposite. Our 1 unit line that makes the angle would be the hypotenuse. And down on the x-axis, we would have the adjacent. And the neat thing about this is that the opposite must be just whatever the y value of this point is. If this is point x comma y, whatever the y value of that point is, that'll be how long the opposite is. And likewise, this adjacent, whatever the x value of that is, that'll be how long the adjacent is. So we end up, if we think of an angle in this way, if we take an angle and plot it on the Cartesian plane like this, we end up with a right angle triangle that we can do some trigonometry with. And because we have a hypotenuse, an opposite, and adjacent, and we're going to know the angle and we're going to know one side, we're going to know the hypotenuse, we can find sine, cosine, and tangent if we wanted to. And today we're going to talk about how we do that. So this is the basic setup. Whatever angle I give you, we're going to work with it this way. The line is always 1 unit in length. So let's keep in mind why we would do this. Well, sine is always opposite over hypotenuse. But if you look up here, the opposite will be the y coordinate of that point. And the hypotenuse is always 1. So this is always going to be divided by 1, because the hypotenuse is always 1. And the opposite will always just be that y value. However high up on the y-axis this angle ends up making that line, that'll be how long the opposite is. So the sine of the angle ends up being just y. Sine theta ends up equaling the y value of the point where that line lands. Right? Because wherever the point is, don't draw this one, but say it were up here and 1 long, this would have x and y coordinates. This would be 1 long. However tall that y is, that's going to be the opposite. And with the hypotenuse being 1, it'll always be the y value divided by 1, leaving us just with y. We're going to look at lots of examples in a few minutes of real numbers for that. Cosine is normally adjacent over hypotenuse. In fact, not normally, always. And if we look up here, the adjacent runs along the x-axis to the point, so it's just the x value of that point. And the hypotenuse is always 1. So here we get the x-axis. And that means we can say definitively that on the unit line that we've made, when we put an angle on the plane like this, the cosine of our angle ends up just being the x value of where that line ends, of the point at the end of that line. And tangent is opposite over adjacent. Now if we look up here, the opposite is always, I'm waiting for you, Caitlin. What did I say, Caitlin? Anyway, thank you very much. The opposite is always y, excuse me, and the adjacent is always x. So we can say here that we can find the tan by dividing the y of this by the x. And even though there's absolutely no reason to rewrite it, just for consistency's sake, I'm going to do it here as well. All right, so there we are. Now, what does this actually mean? Well, it means that we can use this to find precise angles for certain things. And I want to look at just a couple of examples. So if we come down to this unit circle here, we're going to eventually know every point on this circle. But for now, I just want to look at one nice simple point, just to show how we could find the x and y coordinates on something here. So I want to look at this case where we make our angle 45 degrees. Right, that's this line here. So if we swung this line up, so it's at an angle of 45 degrees to the x-axis, we would follow it down like this and across like that. And this would end at some point xy, which would mean that this will be y, this will be x. And because it's the unit circle, because the way we've defined this is we're always going to work with these, making the line 1 unit in length, we say that this hypotenuse is equal to 1. All right. So there we are. Now, let's look at just this specific example. There's lots of different ways you could do it, but this one is one of the nice easy ones. Because if this angle is 45 and this angle is 90, this must also be 45 degrees. Well, if that's true, then these two sides must be equal. And let's redraw this perhaps down below, just to clarify it. So we would have 45 degrees, and the hypotenuse would be equal to 1. I don't know why I made that quite so small. Well, if these two sides are equal, because those two angles are equal, we can figure out how to find them. If this is x and this is y, we could use the Pythagorean theorem to solve this one, and we can figure out what those numbers actually are. So we could say, using the Pythagorean theorem, we could say that, this x squared down here plus this y squared up there is equal to 1 squared. Just a simple Pythagorean theorem question. Well, we also know that x and y are equal to each other in this case, because 45 and 45. So this would be x squared plus x squared equals 1 squared, which would give us that 2x squared equals 1. And then if I wanted to solve this for x, I'd divide both sides by 2. And I would get x squared equaling 1/2. And then, of course, if I want to get x isolated, I have to take the square root of one side. And if I take the square root of one side, I have to take the square root of the other. And I end up with x being equal to 1 over the square root of 2. And now, this may seem really arcane, but mathematicians decided a long time ago that they never like to have a square root on the bottom of a fraction. It's considered bad manners. So what you can do, it's a little weird, but you can multiply top and bottom by root 2. This is just, the answer 1 over root 2 is completely correct, but for whatever reason, we prefer to write it like this, and x would be equal to root 2 over 2. You can check on your calculator. These two numbers are identical. Saying 1 over root 2 and root 2 over 2, those are the same numbers. Well, that means that up here, x is equal to root 2 over 2, and y is equal to root 2 over 2. Okay, so what are we doing here? Why did we do this? Well, that means that for this particular angle, for an angle of 45 degrees, the x value is root 2 over 2, and the y value is root 2 over 2. So we can put that in here. We can say, okay, here, root 2 over 2, comma, root 2 over 2. Those will be the coordinates of this point. Those will be the coordinates of that point. And I solved them using Pythagorean theorem. I also could have solved them using just, excuse me. Sorry. I also could have solved it just using sine, cosine, and tangent. It would have taken 2 steps, but that's okay. We could still solve that. So this is an example of one solving. Eventually, we're going to know how we solve every point on the unit circle. But for today, I'm going to give you the coordinates of each point. The reason being, I want to start working with it first, and then we'll develop it later. So at 30 degrees, which is this first point here, we get an angle of 30. We get an x value over 2 and a y value of 1 over 2. All right, so don't draw this, but if you were to draw this across and draw this over here, it ends up being that this x value down here is root 3 over 2, and this y value is exactly 1/2. Again, you don't need to draw that, but that's how that works. If we go to 45 degrees, we get coordinates, and perhaps I'll line them up actually, like this, of root 2 over 2 on the x and root 2 over 2 on the y. We just solved that. So I just showed you how to solve that particular one here. When the angles are 45 and 45, the sides are equal to one another. So a simple Pythagorean theorem gives us that. And when the angle is 60 degrees, oh my goodness, we get 1/2 and √3/2. All right, so if you look, 60 degrees is actually just the opposite triangle of 30 degrees. Here, instead of going over √3/2, we only go over 1/2, but we go up √3/2. So again, if we define every angle as being a line that swings up on the xy plane from the axis like that, these are the coordinates we get where that line ends. And the last one we're going to look at today is up at 90 degrees, where we get 0, 1. And I suppose it's worth mentioning at 0 degrees, we get 1 over on the x, but no y whatsoever. So that'd be 1, 0. So for the acute angles, the angles between 0 and 90, these are the special angles. These are the angles where on this graph, we can actually calculate these points. We can calculate the exact value of x and y that we get when we do that. And it's not an approximation, it's not a decimal, it's a nice rational number. These are fractions. But then remember, from the first page we said, when we make this thing, y is just the sine of theta, and x is just the cos of theta. So on the unit circle, when we plot them like this, the neat thing is that all points end up being cosine of theta, comma sine of theta. That x value tells you the cosine, because that's what we find here. The cosine is just x over hypotenuse. Hypotenuse is always 1. So the x value will be the cosine, which means that the cosine of 30 degrees is exactly √3/2. The cosine of 60 degrees is exactly 1/2. And the cosine of 45 degrees is exactly √2/2. And the y value in every case is the sine of that angle. So that's why this becomes useful. So I'll just take a minute and check. What's the sine of 30 degrees? Look on the circle. Well, the x value at 30 degrees is √3/2. So sine 30 is equal to √3/2. And that would be the answer to this one. All right, what happens when theta is 0? What about this point? Well, that's okay. That's allowed. Remember that the sine of theta is just its y value. The cos of theta is just its x value. So let's take a look. The sine of 0 degrees, well, the y value here is 0. That would mean that the sine of 0 degrees is just 0. You can check that on your calculator. It's true. What about the cos of 0 degrees? Well, if we look, the x value here is 1. So the cosine of x, cosine of 0 degrees rather, must be 1. And that brings us last to tangent. And if you remember, again, from that first page, we said the tangent would always just end up being the y value divided by the x. It's the y divided by the x. Because when we look at this, it's just the opposite over the adjacent. It's the y value divided by the x value, which means that in this case, at 0 degrees, the y value is 0 and the x value is 1. And that's allowed. 0 divided by 1 is 0. So the tan of 0 degrees is just 0. And you can check all three of those on your calculator. It's true. What about when theta equals 90? Well, let's take a look there. Sine of theta? Nope, not putting theta. We're putting 90. We know theta. The sine of 90 degrees? Well, if we go up and look at the unit circle, 90 degrees is a line straight up, and that gives you a y value of 1. So the sine of 90 must be 1. The cosine of 90, that looks like my dog wrote it. The cosine of 90 degrees, well, let's go look. While this goes up by a whole unit, it doesn't go left or right at all. There's no change in the x value. The x value in this case is 0, which means that the cosine of 90 is 0. Now here, you have to be careful, because tan 90, well, tangent is always y over x, we said. Or we can think of it, if we want, as sine over cos, because y is the sine, and x is the cos, which in this case, the y value is 1, and the x value is 0. And are we allowed to divide by 0? Undefined. So if this theory is right, there should be no such thing as the tangent of a 90-degree angle. Check that on your calculator. See what you get. You should get an error. All right, so we're going to talk about the unit circle a lot in the coming days. Eventually, you're going to have this whole thing memorized. I promise you will. Eventually, we're going to fill it in for the angles greater than 90, which is a lot easier than you might imagine because it just mirrors this whole thing. But for today, the big takeaway for me that I hope you get is that if we look at specific special triangles within the unit circle, we can find the exact coordinates where this line ends for certain given angles. And that means we can know the cosine, the sine, or the tangent of certain angles precisely and exactly, which is a pretty cool thing. So I want you to fill this in from your unit circle. Just go look at the values there. Try to do it without me. I will do one of them for you. Let's say 30 degrees. I mean, I'll actually probably put them all on here. I'd like you to try and do it without me. Pause this video or whatever. If we look at 30 degrees, and we go back to our unit circle, 30 degrees has a y value of 1/2 and an x value of √3/2. Remember, we said it's this y value that is equal to the sine, and this x value that's equal to cos. Right? Because this is the opposite, that's the adjacent. So, for 30 degrees, the sine is 1/2, and the cosine is √3/2. How would you find the tangent? Well, remember that tangent, sine is y, cos is always just x, and then the tangent is just y over x. Or if you prefer to think of it this way, it's just whatever you got for the sine divided by whatever you got for the cosine. Okay, we can do that. Sine was 1/2. Cosine was √3/2. We know our division rules. We can rewrite that as multiplication. That would be 1/2 times 2/√3. And then when we actually do that multiplication, 2 and 2 cancel, and we end up with 1 over root 3. Oh, geez. That was supposed to be a highlighter. So again, I want you to try and fill in the rest of this chart without me. I will put it in here now so you have something to refer to, but please pause this video and try it yourself. Because these are the special angles we should get from this. And tomorrow in class, we will talk about, and hopefully I'll be there with you, but tomorrow in class, we will talk about proving where some of these come from and then expanding the whole thing. So again, try this without me. But if you're back, these come directly from the table at 0 degrees. There is no y. We haven't gone up at all, which means that we've gone 1 over exactly on the x, and the tangent is just 0 over 1. That's 0. That's easy. We already did 90 as well. There we said at 90 degrees, the movement is all up and down. So that's a 1 on the y, 0 on the x, which gives you a sine of 1 and a cos of 0. But here we have 1 divided by 0 is the tangent, and that's undefined. We don't know how to divide by 0 yet. One day. Not today. So those are easy. Then 45 degrees, if we went back and looked at our unit circle, we said, oh yeah, that ends up giving you an equivalent triangle where this side is equal to that side, which means we can use the Pythagorean theorem to solve it, which we did, and we ended up finding that both of these are root 2 over 2. Root 2 over 2. So, in this case, sine is root 2 over 2. Cosine is root 2 over 2. Tangent, of course, is just x divided by y. So that'd be root 2 over 2 divided by itself, root 2 over 2. And anything divided by itself is just 1. So the tangent of 45 degrees is 1. And then 60 degrees is the opposite of 30. Instead of going up by just a half, we go over by just a half. But we go up by root 3 over 2. It's a sharper climb and less of a run. And I'll go show you that back on the unit circle. 60 degrees ends up being a half over and root 3 over 2 up. And again, when it comes time to do tangent, it's y divided by x, or sine divided by cos, so root 3 over 2 divided by a half. When we divide by a fraction, of course, we invert and multiply, so that'd be root 3 over 2 times 2 over 1. And we end up with root 3 over 1. And that, of course, can just be written as root 3. And perhaps because I had to show the calculations, I'll highlight all these final answers. So there we go. So far, these are the angles that we can know the exact sine, cosine, and tangent of. We can know the exact trigonometric ratios of. And we're going to learn more in the coming days. But we'll talk about why this is useful and why it's powerful. But today I just wanted to expose you to it and then have you try some homework questions. So the homework can be found the homework can be found on I just wrote it down, for goodness sakes. $228 numbers 1, 3, 4 seems like a waste of time. That's okay. We'll do 4. 1, 3, and 4. And that's all. I think I told you teacher to go all the way up to 9, but I changed my mind, actually. I'd rather do that tomorrow with you. And even though I'm presenting at Connect in the morning, I'm hoping to be at school tomorrow. I've booked a supply just in case, but I'm hoping I can sneak in. So 1, 3, and 4 is good, and I'll send an email if I remember it to whoever your supply teacher is and see if we can adjust that. So there you are. Good luck. This stuff may seem like it just comes out of the blue and random, but we'll talk. If you want to challenge yourself, I'll show you tomorrow, but I will be super impressed. By the way, Alondra, if you're asking, yes, I do have a prize for you for your lovely work with developing the cosine. If you want to challenge, see if you can figure out how these numbers were arrived at. 1/2 and √3/2. And I suspect you can. You're quite right. So good luck with that. Good luck with your homework. And I will see you hopefully tomorrow. Have a wonderful day.